Hey everyone, today I wanted to talk about how I implemented subtraction into my ALU. You might notice that I still have 4 full adders, which are these 4 columns right here, but I don't have 4 full subtractors. This is because I use a little trick called 2's complement arithmetic to do subtraction for me. Subtraction is already really similar to addition. In a way, they're the same operation. It just depends on if the values being added are positive or negative. Subtracting 10 and 3 is the same as adding 10 and negative 3, right? In binary, this works too. We just need to understand how to get a negative number. Here's one of the benefits of binary. Recall that we have a 4-bit number, each digit being either 0 or 1. We're able to count from 0 up to 15, where our binary number is 1111. What happens when we add 1 to this number? Well, we get an overflow back to 0. Technically, there would be a 1 here, but we can't see it with a 4-bit number. Then we can just keep counting up again. But why does this matter? Well, it means that instead of using negative numbers for subtraction, we can just add by a certain amount and overflow. This is kind of confusing until you see it, so let's go over an example. Let's start with the value 15 and subtract 13 from it. If we have 15 minus 13, we know that the answer needs to be 2. If we start adding numbers to 15, we can see their different outputs, and we just need to find what matches up. We can see that 15 plus 3 would overflow and give us a value of 2. So, 15 minus 13 would give us the same output as 15 plus 3 in a 4-bit binary system. In this case, we can say that subtracting by 13 and adding by 3 give us the same output. Let's look at another example. 11 minus 6 needs to be 5. If we are just adding a number, then we need to add 10. So, subtracting by 6 is the same as adding by 10. Notice how for both of these examples, if we add what we want to subtract by and what we have to add by, we get 16. 13 plus 3 is 16, and so is 6 plus 10. This helps us build a relationship between what we need to add and what we need to subtract by, and we can use this formula to figure out what to add by. The value of x is what we need to add to our number, and a is what we're trying to subtract by. So for our first case, x would be 3, and a would be 13. The tricky thing about this formula, though, is that it uses subtraction itself, so we can't just outright use this in our circuit. We need to look for another pattern. Let's look at these same results, but in binary instead. Now we have a table where the left column is the number that we're trying to subtract by, and the right column is what we have to add by instead to get the equivalent value. It's pretty difficult to see a pattern here, but it becomes a lot clearer if we separate our addition column to be a value plus 1. See? Now these two numbers are kind of like opposites of each other. Anywhere there's a 1, it turns into a 0, and anywhere there's a 0, it turns into a 1. We would call this new value in the right column the bitwise inverse of the left column. This pattern is actually the case for all of our 4-bit numbers as well, meaning that for any of these numbers, we can take the bitwise inverse of them and add 1 to perform subtraction. We can generalize this into a formula that looks like this, where the tilde b, that's the bitwise inverse. B is this blue column that we want to subtract by, and the bitwise inverse is the yellow column, which is what we want to add by. So now we understand how subtraction is possible. We just need to find a way to put this into our circuit. First, let's assume that we have some sort of signal that tells us whether we want to add or subtract. I'm going to call this our subtract bit, and if it's 0, we will perform addition, and if it's 1, we will perform subtraction. Great, so if our subtract bit is on, we need to invert B. Let's put this information into a truth table. If the subtract bit is 0, or in addition mode, then B is unaffected. But if the subtract bit is 1, it's in subtract mode, and the output gets inverted. If we look at this output, you might notice that this is actually just an exclusive OR gate. So, in order to make subtraction work, all we need to do is pass our B input through an exclusive OR before it goes to the adders. So yeah, now if we look back at my circuit, you can see that we have the 4 exclusive OR gates that are connected to these buttons for my B input. The output of these exclusive OR gates goes to the input of my adders. But you can see here that our addition still works perfectly fine. Instead of using the 7-segment display from last video, I just hooked this up to some LEDs. But now, if we move this cable, we turn on our subtract bit. This makes it so now we can subtract B from A. You might ask though, the exclusive OR inverts the output, but it doesn't account for the +1. To handle this, all we need to do is wire our subtract bit into the carry-on of our first full adder. That'll act as a +1 when we're in subtract mode and only when we're in subtract mode. You might also notice that sometimes we have our 5th bit lit up. Normally this is the 16th digit for the full adder, and it turns on when our output is 16 or higher. This is mainly happening because we're inverting our B. When I don't press any buttons, B is 0, 0, 0, 0. This gets inverted to 1, 1, 1, 1. Then we use our carry-on to add 1 to this, which gives us 1, 0, 0, 0, 0. We get an extra bit carried over. This makes sense and is a perfect example of the overflow that I was talking about earlier. But yeah, with this, I've been able to make a calculator that can perform 4-bit addition and 4-bit subtraction. Hopefully you enjoyed my little update going over this progress. Next time, I'm hoping to go over how memory works in a small computer like this, and I'm hoping to make my own. Anyways, thanks for watching, and I'll see you next time.